and this is a part of the Quant Talks series, and also it's a hybrid sense seminar. So let me quickly tell you. So Nagy, I call him sort of like a mentor figure for all of us who are working on oxides. He received his B Engineering Metallurgy, the best department ever, from the University of Pune, and a Ph.D. from the University of Maryland under the supervision of Professor Ramesh in Material Science and Engineering. Following his PhD, he continued his research associateship at Maryland until 2003. He followed this, he then moved to Germany for US as von Humboldt Fellow at Professor Rainer Wasser's group in Juliech. In 2005, he was offered a lectureship at School of Material Science and Engineering, where he is currently, ever since he has in stature, Professor and Postgraduate Coordinator. He has built from scratch a world-class suite of facilities at UNSW in areas of nanofabrication and atomic scale measurements. And the list of publications. Actually, these are the publications we all look forward to reading. Whatever comes from Nagy's interest, all of us working in oxides. So welcome, Nagy. The floor is yours, and dazzle us.
Oh, this I have to mind. Thanks. I kind of hate that summary because I hate that last sentence, which is kind of like chest thumping that I read all of this when there are bricks and everything. Thank you, Pawan, and thank you guys for coming. This is like the largest audience I've had in most talks, in most conferences. I go even invited to talk. It's the session organizer and the guy who wants to close up the room and go. Yeah, I'm here. I'm going to talk to you about a few things that we do in our lab. If you bother to read the abstract, first of all, I'm very impressed because I never bothered to read any abstracts in any talks. But if you bother to read the abstract, the talk is going to be a bit different from the abstract. Abstract talks about two things that we do in our lab now, but then I thought I'll come here and I'll throw the kitchen sink at you. So I'm going to show you almost everything we've done in our labs, but with one material. We work on a couple of materials, but more recently, possibly the last 4 or 5 years, we kind of focused on one material, and I'm going to take that to my gravestone. I will probably only do one material for my entire life from now onward, as long as I get funding to do that. And that material is bismuth ferrite. So I'm going to show you a lot of things that we've done with bismuth ferrite. A lot of this is published work, so I couldn't show you things that are not published because of sensitivity issues and recording issues and things like that. And it's not really very new. It's not very old. It's not as old as me, but it's not as young as you. Most of it. So if you have any questions, please stop me and ask me rather than wait for the end of the talk, because it's a lot of concepts and a lot of content, but small packets, and we'll switch applications and topics. So you're not going to be able to remember things at the end of the talk. So if something is not clear, please stop and ask me. Specifically students, students, we should encourage them to ask questions. Challenging questions. I'm not at any obligation to answer those. At least you can ask the question. Okay. All right. Here's the outline. I'm not going to give you a summary of publications, future directions, etc., because it'll be there. And it's kind of in the intermediate conclusions. I want to give you a brief introduction to what we do in my group. Normally, people I talk to and give talks to these kind, not all of them are familiar with oxides and epitaxy. So I have a couple of slides of oxides and epitaxy. Then a little bit of introduction to ferroelectricity and bismuth ferrite. And the funny bit is that people who do ferroelectrics for their life often forget some of the nuances of ferroelectricity. So it's quite important to kind of appreciate that fine link that we will sort of deal with much later. Then most of my talk is going to look at how we've used bismuth ferrite to do electronic devices. Now, I am not saying that the laptop you can buy from Reliance Digital tomorrow is going to have bismuth ferrite in the device that I'm making. It will never have it till I die. Even from 50 years from when I die, I don't think bismuth ferrite on strontium citinate is ever going to become a device. But the the aim in our lab is to grow really clean materials and try to understand some fundamental device properties. What you do after that, sometimes like someone like Pawan takes it to a system like Hafnia, which is a lot more translational with silicon, tries to make a device similar to that. Some people like the fact that we're growing dissimilar materials, they try to kind of emulate that. So there are other flow-on effects, but it's not very likely that you're going to make a mousetrap from something that we do in our lab. And I don't think there's any shame in that. After that, I'll come to possibly 4 or 5 slides for which Sujit is waiting for. So you can actually go home now and come home later. To be honest, is very simple, but this is something that we are really proud of because I'm not overstating this. From 15, when the first set of these structures are found in lead titanate, there's been like this global race to show them in bismuth ferrite. And there are some nuances that people missed that we were very lucky to catch and exploit. So hopefully I can go over that with some detail. Okay, I don't think a summary of some of this outline was actually done for a program review. So I'm sorry, the summary of publications is not really important. We always have to thank people who allow us to do this amazing research. So last 7 years, I've been part of a center of excellence called Future Low Energy Electronics Technologies, that's FLEET. So you can look at our website. This is about 20 faculty members across 7 universities. We've got a lot of money to work on fundamental problems, to look at different alternatives to low energy electronics. And the motivation is simply, we will come to a point where we cannot spend the amount of energy we are doing on normal computation as we are doing now. Most of my other funding comes from this program called the Discovery Project, which is our version of DST. This is kind of information irrelevant to the students, but the faculty members are interested. I had some small grants from DARPA and ANSTO's, our neutron organization that supports now 1 student with me. And then I also have another, so the CSIRO is another research organization that is supported by industry, and there's a postdoc with that group. But I will not be talking about that person's work. They just started. It's kind of fun. Most of the work I'll be presenting today is driven by the 4 people. Other than me, I don't do anything. I just stand and smile and pose for photographs. Daniel Sando used to be a postdoc in my lab. He was with us in FLEET for about 6.5 years, and now he's starting as an assistant professor in the University of Canterbury in New Zealand. He's looking for good PhD students. So if anybody wants to, anybody thinks Bangalore is too boring for them, they want to go to New Zealand. Oliver is the person, the student who was with me working on the offset BFO, and we will talk about this. So he's in France now. He's doing a postdoc with Manuel Bebes. So people who know the Oxides community, Manuel Bebes is a pretty big guy. So Oliver is doing some spin effect studies on BFO with Manuel. Vivasha, whose work is all about solitons and bubbles, a lot of things that has been done in the last 5 years. Vivasha drove it, and she did the smartest decision. She got the hell out of academia and went and joined the bank. She's probably making 5 times as much as Alex is. Okay. And Peggy is the magician. I call her the magician in my lab. She makes things happen. She just started a research fellowship in the another national lab, which is in a neighboring suburb. So she's not in UNSW anymore, but she's got a visiting appointment. And a lot of the work here is thanks due to Peggy and Daniel, because these guys really took care of the group. They took care of stuff, and if I'm freaking out, they calm me down. They kind of say, relax, they teach me breathing techniques, things like that. So it's very important to have these kind of people in the lab, I feel, who can take care of the students, linked to the professors. So I'm very, very grateful and fortunate to have these 2 people. And I've been telling the younger faculty members I've been meeting today is that when you start off your career, you are interested in buying toys, but over time you realize toys are not as important as warm bodies. So I put a lot of effort in building relationships with people rather than focusing on toys. Okay, so what does my lab have? So I was very impressed with SENSE and its facilities. We are not as well endowed and as rich as SENSE in any manner. So we have a couple of pulse laser deposition tools, one that is made by Neocera and the other one that is made by Pascal. Reasonably standard pulse laser deposition tools, except that in one of the Neocera chambers, the target to substrate distance is quite large. Normally, when you design PLD chambers, it's 5 to 7 centimeters. We have it kind of almost between 12 and we can go up to 15 as well. But for most of our depositions, it is between 10 and 12 centimeters. And the effect of that is that our growth rate is so slow that 70 nanometers or 70, 75 nanometers is the maximum we can grow in our lab. Okay. So I'll have somebody come to my lab and say, I want to make a thin film of some material. And I'll say, okay, nice, great. I want to make it as well. How thin is your film? Oh, it's very thin, only half micron. I say, okay. And then you have to make a documentary and big LEC, not a film with my chamber. Okay, so they go away very quickly. So we can do up to 70 nanometers. And our basic interest is on the other side. I want to go 1 nanometer, 2 nanometer, 4 nanometer. That's where the physics is in terms of what we are interested in. So once you grow it, similar to your SENSE structure, we have a central analytical unit where we do X-rays and stuff like that. But we've got also a cipher. So I've got two AFMs. One is a multi-mode 1994 AFM. So the central microscopy unit was going to throw it away. So they called me and they said, either you can pick up a 94 AFM or we'll throw it in the garbage bin. What do you want to do? So I went ran, picked it up. So we've got a 1994 AFM. When I picked it up, it was still running Windows 3.1. So I had to upgrade some cards. The hardware is amazing. So I upgraded some cards and now I'm running on the latest Windows one. But that's like the instrument the new student starts to learn on because nothing is self-aligned in that. So the student has to learn how to align the laser, how an AFM works, how to land the tip, how to put the tip. That AFM does not cooperate with you at all. Okay, so you have to literally, my advisor used to say, in Hindi it's like sadhana. You have to do sadhana with that instrument for many, many months. And then slowly it will give you results and incredible results that will. Okay, so then the other AFM we have is a fancier one. It's a cipher tool. I don't know if your campus has got a cipher, but cipher is one of the best AFMs in terms of resolution, stability. And a lot of the images I'll show you later on with this technique called CFM is primarily possible because we have this DART mode, which is dual amplitude resonance tracking mode in the cipher. So I'm not advertising cipher as such, but there are different AFMs. What I'm trying to get across is there are different AFMs for different things. And if you're fortunate enough to be in a center where you have the idea of the ability to get these different tools, then you should exploit that. We just installed a cryogenic probe station about 6 months ago. We don't have much data to show for that, but I know it works because we got some PE loops at about 100 Kelvin, and they're nice and square and sharp, and they're believable. So hopefully in the near future, we will start to throw some data on that as well. I want to talk to you about the quantum tunneling diode devices that we've also developed because it's just too much time and too much talking and it's not in business ferrite. But we are trying to develop that in business ferrite now as well. This is also a project we are trying to do with Pawan here, where we are trying ideas to use hafnium and see whether we can design resonant tunneling in hafnium. So hopefully it'll give me more reasons to come back to Bangalore and visit Pawan. Actually, District 6 is a better reason, but Pawan is all right for the people who approve my plan. Okay, so what do we do in our group? So the fundamental philosophy that we use in our group. And this is a really beautiful line that I took from this nature materials perspective, that 1 and 1 is greater than 2 in oxides. So this is a recent strategy that has absolutely been driving my funding my research since 2005, 2006, right? So we are obsessed with taking things and putting it in layers and finding out what happens when you put it in layers. So the number of examples is just, innumerable. The most popular one probably in terms of general condensed matter physics is LaOSTO. You take LaOSTO, you take two insulators, you put them together at the interface in superconducting. Right? So oxides give you that ability that you can layer them very well, particularly perovskites. So the perovskites give you that ability that you can layer them with atomic level precision, and the result, this resultant system can have properties that neither of the constituents have. Right? So that is a really exciting way to develop new properties or to develop new kind of physics in existing material systems. Okay, so that leads on to my next slide, which I think this image is quite popular in the oxides community. Is these layers with balls that stacked up, and what can oxide heteroepitaxy offer? Maybe I'm preaching to the converted here. I don't know if there are people who don't do oxide heteroepitaxy, but if you're not familiar with that, it is one of the most powerful ways to have controlled growth in your desired orientation. You can tailor the structure, and not every system. The one thing that I try to get across is that not every system needs to have atomically sharp interfaces. In fact, there are some systems where our goal was to not get atomically sharp interfaces. So we like the classic example is strontium ruthenium oxide, which is a electrode, and then you grow PZT on it. But if you grow it very slow, the titanium from PZT starts to replace ruthenium from strontium ruthenium oxide, because ruthenium oxide evaporates. And the top layer, so strontium ruthenium oxide is an electrode, and the interface, which is this diffused interface, is a semiconductor. And then you have a PZT, which could be it's a good semiconductor, it's a really good insulator. So there, we don't want atomic level sharpness, but we were able to do this buried interfaces by design. So that is something that oxide heteroepitaxy really offers us. The other thing that we can do, and I was talking at lunch about it, I don't have a slide here, is that not everything has to be a film. So, when we first started growing bismuth ferrite, we were struggling like everybody else, and we used to keep getting this iron oxide pockets, right? So when I was a typical PhD supervisor, I was just driving my student crazy, saying, I want perfectly smooth bismuth ferrite films. So we got to work on that. But the student is obviously smarter than me, because he said, why do you need bismuth ferrite? Look, I can get you iron oxide at scales and sizes and shapes that nobody else can get. And the fact is, we can exploit bismuth's volatility. So if you don't know, bismuth is got a very high vapor pressure. It's like lead. Now, you don't control the atmospheric, you don't control the chamber pressure, you will lose bismuth, right? Now, the rest of the world is obsessed with controlling that evaporation or sublimation of bismuth. They don't want bismuth to leave. We're in Australia, right? We do everything other than the northern hemisphere, right? So we said, you know what? We want the bismuth to leave. We will let the bismuth go. We don't want any bismuth in our system, but we can control it such that the bismuth in the form of bismuth oxide, which is like a liquid, separates from the B-side oxide. So in this case, it was iron oxide. And you cool that in vacuum, all the bismuth goes away, and you are left with perfectly defined iron oxide nanocrystals, okay? With very tight spread of size and beautiful orientational relationship to the substrate. Now, if you can do that in iron oxide, why can't I do that in bismuth nickelate, bismuth chromate, bismuth manganite, bismuth whatever? And that's what that student did. He took any Bi a Bi transition metal oxide, and he showed that you can make lovely transition metal oxide nanocrystals just by controlling the epitaxial growth conditions. So this is something that is actually quite difficult in other approaches. Okay, so obviously I'm touting my own kind of technique, but I do feel that the opportunities are just simply amazing with the oxide network attacks. And then the crystals are actually epitaxial to the substrate as well. So they're not shake and bake. They don't have like infinite surfaces or whatever. They're very well defined surfaces that we could then study for their individual surface properties. I won't go over this slide because I think most people know here what Ph.D. is based on what I've seen. But if you come to our laser user facility, we've got another laser MBE system, which is basically laser read, and there you can do lanthanum. So there's one dedicated chamber for LAO-STO type structures. There's another one where we do manganites and other things. Okay, so so the nice thing with PLD is that you have one laser, you can do 3 or 4 chambers, but and you have 2 labs and 3 lasers, and it becomes 6 chambers, 8 chambers, and so on and so on. The other thing that we have unique in one of our chambers is the ability to have a temperature gradient. So one of our the Pascal laser chambers, because the heater is a laser diode heater. So if you're not doing thin film epitaxy, you find all of this boring, and I apologize for that. But if you're doing growth, I asked somebody over here, I think I asked Ashar, yes, well, how's your heater? And he said silicon carbide coils, right? So that's a standard heater. So if you, instead of have a coil heater, think about having a solid state laser that is all then put onto an IR sensitive silicon carbide block, which absorbs the laser and it heats because of that. Now you chop that block into pieces and you can say, I can heat this block, this block, this block with this power, and I can heat the other block with another power and so on and so forth. That gives us the ability to have temperature gradient in a single substrate. So the idea is you grow one film. One side of the temperature is 800, for example, and the other side could be 600. And then, you have this complete spread, and you don't have to do 100 samples to do the best temperature. I mean, in theory, that's the idea, but in practice, it's not that clean. But we've done a couple of those optimizations. And the other thing that we use in the not in my lab, but in the one that is dedicated to LAO-STO, is we have the scanning read. So I'm not so sure of the read guns that you have here are spot or they're scanning. But if you have scanning, the advantage is that you can choose 7 locations or 8 locations, and each one that will give you a read pattern. So you just choose the best read pattern for your paper. That's the thing. The beam actually rasters over the read gun is also now rastering over the sample. So it's quite an interesting kind of approach to look at growth. Okay, so I don't want to go through this because I was not expecting so many PhD people, but this was probably. Just to go through this very quickly, one of our chambers, you can, so one of our collaborators, in France, you grow the same bismuth ferrite target, same materials, almost the same substrate, etc. Just based on how the growth rate is, we can obviously control how the surface is. So if it's a very high flux, so this is Manuel's in Manuel's lab. If we do bismuth ferrite with the neodymium YAG laser, we get a rough surface, and we've shown that that sample has got a lot of internal strain gradients. So the flexoelectricity in that sample is quite high. We put I put sodium ruthenium oxide LSM over here. But we can get that kind of growth with bismuth ferrite on a layer in one of our chambers. The one that has got the large display distance, that growth is so slow that we end up getting bismuth ferrite with almost 10 days. And that becomes quite important when you're doing superlattices, because in that case, you're only having few nanometers, and you can't have these rough kind of height profiles disturbing the electrostatic boundary. Okay. All right. So with that, I'll go to the first kind of device topic that we've done, which is ferroelectric domain wall memory. So what is ferroelectrics? Most of you will know this. If you take something like barium titanate, which is the canonical ferroelectric, we've got 2 or more polarization states that can be switched with an electric field. Right? Everybody knows this. Which means it must have a spontaneous polarization, and the PS can be switched by electric field, 2D materials, etc. We see papers on that in all these fancy journals, and often it annoys me because this is something that is not proven unequivocally in many of those systems. Why bismuth ferrite? Bismuth ferrite is a ferroelectric, but of course it's also multiferroic from the iron. The spin comes from the iron. So if we control both the electric and magnetic field, the holy grail is that we can kind of manipulate the magnetic moment by switching the ferroelectric polarization. I think in the beginning, a lot of people tried to do that, and then we now know that the coupling is not direct, it's kind of cross-correlated, and the coupling is not as straightforward as people originally envisioned. And Sujit's former lab, those guys have published a lot of nice papers now on the magnetoelectric phenomena in bismuth ferrite. So the important thing is, bismuth ferrite, unlike barium titanate, is a rhombohedral system in its bulk form, which means it forms different sets of domains compared to barium titanate. So like I told you, nuances about ferroelectricity. Most people write nature papers, but they forget the fact that the domain structure should be correlated to the crystallographic structure. And then you find some papers claiming quite impossible domain structures not related to the crystallography of the system. And then you ask them in a conference, like, can you explain to me the underlying crystallography of the system? They don't know why you're asking that question. And then it's a bit annoying. So in BFO, we have these 4 types of domain walls. And they are important because some of them will conduct and some of them do not conduct. So this was my colleague Jan's breakthrough work when he was in Berkeley, where he found that if you have 71, I always mix this up. So 71 is conducting, right? It's not as conducting, and or 109 is conducting, and 180 is not. And you'll see that in next slide. So can we then kind of engineer the ferroelectric state so that we get only these kind of domain walls that conduct? Right? That was the purpose of this topic, ferroelectric domain wall memory. Why do we want to do that? Because we thought that if you have a ferroelectric domain wall as a switch, a domain wall that conducts, then if the domain wall exists and the circuit is closed, you'll have a low resistance state. The domain wall can be erased. If the circuit is open, you have a high resistance state. So you have a very easy 2-state memory, 0 and a 1 state. In a very simple design concept, the wall is there. It is a, let's say 1. I erase the wall, it's a 0. Okay. Now, easier said than done. It's not so straightforward to get these conducting domain walls in other ferroelectrics, but with bismuth ferrite, for a number of reasons, we have this very beautiful system where one set of walls conduct and the other one doesn't. Which means if you know how to grow bismuth ferrite well with the desired walls, you can then start to play, we can start to think of this memory structure. Why walls and why not the ferroelectric itself as a memory? Well, the wall itself is quite thin, it's quite small. So if you're really talking about density, you can achieve densities that are quite impossible by just using the ferroelectric portion itself as a bit. Okay, so you have a ferroelectric domain, up or down domain that is separated by a wall. The domain itself can never be stable at that size scales compared to the wall. So the way we push this is that we can get really nice density because the width of the wall is so small. And because they are unlike magnetic structures where a proximal probe reading and writing is actually it's done, but it's a bit complex. In a ferroelectric system, the proximal probe writing works very well because you have an AFM tip, you apply a bias, you can create a wall. You apply another bias, you erase the wall. So you can get a really nice on and off state like that if you know how to do this correctly, which is what we did. So the innovation here, and this is something, again, when you look at our resources, we are a small lab in a corner of the world fighting against these big global giants, right? So the only way to win that battle is a David versus Goliath battle, is to become innovative and think outside the box. So what is it that we did? Separate to almost everyone at that time who were trying to achieve the same. Is that instead of growing 001, Pankaj, who was the lead postdoc, came up with this brilliant idea saying, actually, we should grow on 110 because then we can control the wall orientation much better. And he was bang on. Simply growing the BFO on 110 gave us that edge. Okay, nothing sophisticated, nothing, no fancy calculations, etc., etc. We said, okay, 110 supports this kind of wall. We'll do that. We won't have a bottom electrode. The polarization will be in plane, and we'll just use in-plane coupling to write and erase. It's possible. And that's what we did. So you see here, the BFO is grown on a bottom substrate, but there is no bottom electrode. I know at this time, a lot of big groups were actually having bottom electrode and they were trying to do out-of-plane switching. In-plane switching, actually, if they had done this, they would have won this race rather than us. And you can control that in-plane switching by simply controlling the space between the small electrode and the ground electrode. And you can control the size of that small electrode so that you can control the electric field distribution. You can do all those things. So we made e-beam devices. This is not very fancy three-step process or something. Peggy, again, was very patient. He was just getting the PMMA dosage conditions right. So then you just write a big electrode and we write many, many small electrodes, and you just platinize what you've written, lift it off, your devices are ready. And what we do is we make use of the fact that there is a very strict orientation relationship between the polarization, the crystallography, and the electric field to have a controlled creation of 71 and 109 degree. We actually did both. And it's shown up here that in the as grown state, this is a PFM image. The out of plane image shows that when I grow it, all the out of plane orientation is in one state, and all of the in plane orientation on the right side, that's in one state. The moment we apply a bias on top of the electrode, there's a 300 nanometer electrode that is sitting up here. You can then create switching, a correlated switching, where it creates a domain wall, and you see that arrowhead kind of shape of a domain wall that is created. And that domain wall is going from that small electrode, it is going all the way to that big giant electrode. What happens if that wall is conducting? It's very simple physics, right? If something is conducting, it's shorting between this and this, and you apply a current, then you should be able to measure it. That's what our conduction AFM images show. The moment you apply a bias, you create that wall, and you look at the current map, it's an on state. Now, that on state is also controllable. It depends on the shape of the wall. So you can get this really nice controlled creation of many states that are lightsaber. Controlled creation of this multiple states of conduction. It's a very elegant and very simple idea. So this was, I mean, this is really, I was really shocked at kind of how well this idea worked, you know. I think I've been in this business long enough that I know that if you have an idea and it works, then something must be wrong. So, and when the wall is not there, absolutely no conduction, no current over there. So we do the cross sections. And our on-off ratio is reasonably good. It's about 1,000. So for a prototype device, it's pretty good. So
stopping you from going high voltages?
Couple of things. One, the tips, because there is current flowing through, there is resistivity, the tip gets burned out. And B, we already proved it's saturating at 2. So really we are not, I mean, what new physics am I going to get? Right? So maybe we can. The retention characteristics. So if you don't know what is retention, you know, when you present a memory state, they want to make sure that whenever you store it in a memory, it remains for a while. So we showed some retention data, 10 to the power 4 seconds. Of course, apnea, Pawan's apnea people want years. That's a different story, but we showed that it's not just a metastable wall state. It is actually there for that long. What stops us at 10 to the power 4 seconds? A, the postdoc wanted to go have food at some point, and B, the tip is not stable. We don't 10 to the power 4, it also gets worn off. The problem is the probe-based measurements, right? So if you take the tip out, put the tip in, if you've done AFM or those kind of things, you know, it's not that easy, it's quite cumbersome. We also did endurance measurements. Of course, if you look at the standard fatigue data in a ferroelectric memory or in any other memory, they want to go to million cycles. Here again, the tip can only go up to about 800 or 1,000. That's enough for us. Basically, it showed very well that our idea of this domain wall memory worked very nicely in this model system. So then we went to the next problem. Now that we can write and erase, can we control the shape and we control the type of domain wall? So the first paper actually talked about non-charged domain wall. Then Pankaj created charged domain walls and then a mixture of domain walls. So you can see that based on the type of the domain wall, you can actually also control the type of conduction. Very beautiful example of understanding transport, or like rather creating transport at that length scale using probe-based techniques in a multiferroic. I mean, imagine other possibilities. So what are we trying to do now? We want to see eventually if we can show that we can use these domain walls for everybody wants to do neuromorphic computing these days. Why not us as well? Okay. How can domain walls be used to understand one-dimensional transport? And I'm so excited because I found more important than power is a student of his who can help me understand the stochastic spikes in domain wall transport. So he's going to hear a lot from me, and I'm not going to bother him. He's going to curse Pawan, but it's not my problem. And what we're also trying to do is now, or I would like to do is to understand, can we change the length, the type, and then get these, multiple levels of data storage in a single kind of architecture. So that's a bit complex, and I'm not so sure when I'm able to do that. It's in the pipeline. But is it Vivek or Vivek, right? Vivek, I'm so excited that you're doing this. So. Okay, so let's go to the next thing that we did. We looked at how to write ferroelectric memory with a long-term retention. Okay, so it's kind of different from the previous concept. The previous concept we use walls as the memory. Here we're using the actual ferroelectric memory system as our memory state. And the reason we wanted to exploit this is that we looked at the fact that probe-based memory was done before, but there was this problem that either they had a density issue or they had a time dependence issue. If you got it really dense, really small bits, then kind of they wouldn't be stable over time. But if you want to write bits that are stable over time, then you couldn't write it very, very small. So how do we solve this problem? So this is where I don't know if Bhagwat is here, but I told him that the PLD that we have in our lab, nobody else can do that because this PLD gives us amazingly defective films. So, but we exploited this. It's again the PLD with the long throw distance. And what we find is that because the growth is so slow and bismuth is constantly being lost, so we have to play around with the target of chemistry. When you grow this bismuth ferrite on lanthanum aluminate, now why lanthanum aluminate, etc., please bear with me, I have slides for that later on. But when you grow bismuth ferrite on lanthanum aluminate puts this compressive stress, and that it extends the bismuth ferrite out of plane. It completely changes the crystallography of bismuth ferrite. And in the breakthrough paper from Ramesh's group, when they do it, that strain is only sustained for 10 nanometers. Actually, those guys even at 5 nanometers, they're getting what's called mixed phase. And this is the classic thing that happens in most chambers. I think Sujit's chamber, Pawan's chamber, everybody else's chamber will show this, I can tell you. You grow and you start to see the small specks. This is the mixed phase, the R phase nucleating, and eventually you will have this really well-defined striation, which is basically this system has got R and T phase, rhombohedral and tetrahedral. For our chamber, because of the growth rate, which is being so slow, it's losing bismuth. So what happens is that you start getting these stacking falls, where the loss of bismuth means that you have the iron oxide stacks on itself, and then the bismuth oxide stacks on itself. Okay, so you have a self-correcting mechanism where you start to get these entire array of stacking faults such that there is, and the stacking faults are also, so they are imposing that lattice strain. So the system, it's a very beautiful example of how nature manages to self-create, self-accommodate. So bismuth oxide is imposing the same strain as the underlying lattice, underlying substrate, sorry, such that through the entire thickness, you will not find there is any relaxation of dislocations or mixed phase. So it's T phase, it's the tetrahedral phase, the right up to, we've gone up to 100 nanometers, but above 70 nanometers, what happens is the surface begins to deteriorate because the bismuth now is really going through the surface. It becomes quite pitty. So 70 nanometers will give you some really nice stripes, and then around 70, you can start to see sometimes there will be these small pockets. So this X-ray is not very, very impressive, but if you look at those papers, then you will find that very nice satellite reflections, and the T phase is like a really clean and beautiful interface and rocking curve and things like that. 15 minutes. Okay, I will really talk fast. Yeah. So you take this system, right, and start to write the bit on this system. We found that those defect pockets actually stabilize. They are pinning centers for your bit. So our retention time eventually is something like our activation energy for that retention is about 6 times. And then the student basically came back after a year and he still found those bits written. He was doing some other experiment. He said, okay, I had some time, I'm going to do a PFM, and he found those bits are written. Okay, so I can tell you now the paper was written completely in a reverse engineering manner. We found the bits written, we were like, wow, the bits are still written, why are they written? And we found that the defect stabilized. Right? So this is a really nice example of kind of where, that's why we call it like designer defect. The defects are like, well, somehow they're like it's a positive attribute, like I'm a designer defect. It's not like a, oh, gee, that. And you can see that there's clear diffraction contrast. There's quite a bit of this. And we have now a follow-up paper is going to come where we actually completely analyze the crystallography of that defect. So it is kind of what we.
Can you play with this now?
They
Written. Like, can you highly feel that?
erase it.
Erase it.
Yes, all kinds of things. So you can push it. So I don't know if the student now is a postdoc, whether one thing that you could do is do something called tomographic AFM. So push it with force and see whether those defects move and things like that. So yeah, all those possibilities are there. Gary, I think that's the other question you want to do. What can I do to write real space topologies? That's kind of where that's where we're going. What else can we do? Of course, this is a philosophical question. Is it practical or is it just time collection? Actually, I don't care. Physics is really beautiful, but you know, when you're promoting this to a program director or program manager, they want to see whether it's really possible. Okay, now last 10 minutes, showstopper for solution, right? So topological defects in bismuth ferrite thin films. So I won't go into the details of what bismuth defects are, but the idea that topological defects are this is fermions and all that, it's like they're an extreme case. Even a domain wall is a topological defect. We didn't know that. So the first part, I'm going to show you how I can actually engineer new domain walls to help me get new properties. Okay, and the idea over there, I've shown you like probe-based devices, domain wall devices, but what else can we do? So coming back, you have to remember that BFO has very strict domain orientation related to its crystallography. So if you change the crystallographic structure, you will change the domain structure. So this is something that anyone studying ferroelectrics must remember and must never forget. There is an intrinsic link between the domain structure and the crystallographic structure. All that postgraduate students are made to go through this mathematical exercise to prove that, so they never forget it in their life, even if they're joining banks. Okay, so you have these different types of domain structures, but the important thing is the polarization is tilted in BFO. It's not in its bulk state, it is a tilted polarization. It is not a normal polarization along the C-axis. So any games you play along stress or boundary conditions, you got to take into fact that polarization is already tilted. Okay. What can you do mechanically? So I told you I'm going to tell you what this R phase and T phase and why LAO is. When you grow bismuth ferrite on a substrate which imposes a large compressive strain, you go through a series of crystallographic changes in the material. Okay, so this is quite popular in heteroepitaxy, right? We do strain engineering. That means we use different types of strain to control what is the over crystallographic phase that is resultant based on the strain. A lot of people have done that. But what is not done so common is how can we change the orientation direction? Okay, most people will use the three common orientations in perovskite heteroepitaxy. They use 001, the 110, which I've shown you, the domain wall device, and if it's a FCC structure, they may use 111. So there are some nice papers that look at growing nanomaterials along these three directions. But what about other miscut directions that are along this over here, which means it is not tilted fully towards a 45-degree 110 plane. It is not fully normal. Can we push the polarization to a unique axis? That'll give me a new domain state, a new domain wall state. So that is what we did in this work. So what we said is that if you look at the 310 state, so we did some kind of what is called Gedanke experiment. we find that something like the 210 and the 310 they are the ideal. Sorry, the ideal miscut directions where you will find that the polarization of that phase actually tilts. It doesn't relax. Okay, so you cannot have it relaxed by the normal strain relaxation mechanism by ferroelastic domains or dislocations. I mean, you know, if you should all know by now what are dislocations, right? So what we found is that 18.4 degrees, which is close to the 310, is excellent for pushing that polarization on the brink, which means anything more, it will say, you know, to hell with you, I'm just going to relax myself with ferroelastic motion, ferroelastic domains, and go back to my bulk state. Right? So we're on the brink, which is great because that's exactly where you want it to have be when you want to have large piezo response or large any large susceptibility response. So how does it look if you grow it on 100? As I said, on lanthanum aluminum, you get the standard mixed phase. You grow it on 110. If you've done 110 growth, you get the stripy phase. But you grow it on 310, you get something that is somewhere in between. Okay, and we call this phase the super R phase, the super rhombohedral, because it's not really tetragonal, it's not really monoclinic, it's not really rhombohedral. It's actually a rhombohedral phase that is under 3.7 compressive strain anisotropically in the AB plane. So there's a very complex crystallographic state where one axis, it is allowed to relax the strain by dislocation formation. And the other axis, it is not allowed, it has to tilt. And the net result of that is that you get the new crystallographic phase of this ferrite with a tilted polarization. Now, if you're familiar with piezoelectricity, tilted polarization is great news because if you have tilted polarization, when you apply bias, you can kind of rotate it, and you get a large piezoelectric coefficient. So that played very well into our idea, right? So I'm really kind of proud of this work because this is all of Daniel Sando's baby, because this is not serendipity. You know, most of the good experiments in our life come from serendipity, but this is where he actually sat down, he designed it, and it felt exactly how he predicted. So there's a lot of pride in this work to see that something that you think in terms of concept has actually come true. If you want to measure the piezoelectric response of this film, we do PFM, but one of the problems was how do we separate the artifacts, because it's quite rough. So you have electrostatic contribution to the dip other than the pure piezoelectric contribution. So instead of using the optical beam deflection method, we use this method called an interferometric displacement sensor, which is something that Oak Ridge guys have developed with Asylum. So instead of having a laser beam that measures the angle on the detector, it actually measures the displacement using an interferometric system built inside the tube. Okay, so we sent a student and a sample to Oak Ridge. They got really nice data, and we know that the displacement measure is very accurate, a lot more accurate than the normal method of PFM detection. This was important because we were claiming that our piezoelectric coefficient is very high compared to normal BFM. So if you want to claim something like that, we got to absolutely make sure it is really high and there are no spurious effects. So we do get that. We find that our film, so you got to remember our films are still under clamped constraint. So our RBFO itself is showing around 12 picometers per volt, and the super RBFO is about 3 times larger. Okay. So we are very confident that this is a new, like, quite elastic form of bismuth ferrite, which has got very exciting piezoelectric properties, and we will do a lot more work on this in the coming years. Okay, now the other way to introduce topological defects, and probably something that all of you will be more familiar with, is to create these curling structures. Right, it's a very fancy topic now. Everyone doing ferroelectrics is into this topic, and everybody's finding bubbles and domains everywhere. So it's a bit scary that everyone is reporting these things. Anyway, how do you get this curling structure? The first kind of unequivocal evidence was for lead tightening. Right? I don't have time to get into the absolute nuances of that, but what we need to understand is, first, you got to exploit the phase versatility. So lead tightening, go back and read the paper. Now, I want you to go back and read the paper. It was shown on dysprosium scandate first, not on strontium titanate substrate. There's a whole set of papers on lead titanate, strontium titanate superlattices. Look for many other things, Matt Dauber and Pablo and all these guys, they couldn't find it. But why is it that Ramesh's group saw this first? Because I think the important thing is dysprosium scandate was used. So very important point over there, because dysprosium scandate gives the right amount of tensile strain on lead tightening to slightly pull the vector from out of plane to slightly in plane. So you got to understand the phase versatility of your crystal structure. Okay, so this is what we did. We said that if you have R like BF4, which is the bulk rhombohedral structure, which is already tilted, right? You put tensile strain on that. These guys from Berkeley tried to do it on DSO. They already used tensile strain. It is going to just make more, actually forms very nice flight domains. So the first idea is that instead of tensile strain, push the vector out of plane. So make it closer to 0, 0, 1. How can I do that? You use lanthanum aluminate substrate. It's possible. Now, the challenge here is, normally, you put in a lanthanum aluminate substrate, within 5 nanometers, 7 nanometers, you got nucleation of the mixed phase domains. They relax that strain. That strain cannot be relaxed. Under no condition should that strain be relaxed by this ferroelectric or nude grouping. I wouldn't say ferroelastic, but this other strain relaxation mechanism. But we want it to form like a curling structure, right? How are you going to get that to happen? You exploit the fact that when you grow it very thin, the polarization cannot be sustained, and the system is going to try to kill the polarization. So that means the depolarization plane is the depolarization field is going to try to make the system go from out of plane to in plane. Okay, so then you have a polarization mismatch, and that minimizes the depolarization field. But how do you do that? You have strontium titanate to something like strontium titanate that pulls the polarization in the plane to create this effect, but you want something like lanthanum aluminate to stabilize the out of plane polarization. So do something like the other guys did, do PTO, STO tag, just do an epitaxial superlattice, but make sure that you never relax the BF4 layer to form mixed phases, which means we can do this experiment only in that chamber with the long throw. Any standard PLD chamber, I think, is not going to give you these structures that easily. I may be wrong, and I'm happy to be proved wrong, but I believe the reason we solve this compared to others is because of the fact that we got this chamber with the long throw. And in this paper, one of the things we did very well, I feel, is in this particular Nature Comms paper, the first 2 pages, we spent a lot of time explaining the rationale of our approach so that people can not just understand it, we would like it to be repeated and can kind of give affirmation that our understanding is correct. So once you get these 2 combinations right, then the next idea is the next challenge is what is the design of the superlattice. So for that, we did a whole lot of growths, and we find that there is this sweet spot. If you grow the bismuth ferrite layers too thick, then they will not form solitons and actually form beautiful labyrinth domains. I don't have that image here, but it's like just spectacular labyrinth domains. Which are the Nature paper that Martin, all these guys published. If you grow the BF4 too thin, then it's actually reaching the point where it's like a smeared dielectric. The polarization, it doesn't have very good polarization. And I think this is a very, very interesting system itself. So we are going to send you the sample as well, because I think this may be on the verge of some kind of smeared phase transitions. Really, really something that is exciting, and not many people can do this kind of systems. So when the student took the image, I was like gobsmacked when I saw this image, because I'm someone who remembers word by images. And this looks like exactly like the Muller. There's a science paper from the German group on magnetic systems from Muller and the guy from Dresden, Lucas Engg. So Lucas Engg is a co-author, and they see the same kind of patterns, and they see these juncture points. So we started looking for this, and lo and behold, we see similar things. We see a discrimination center, we see half neuron, we see target fermions, we see all kinds of different topological structures in this thing. So one of the referees asked this question: why is it that the PTO STO guys see very clean vortices or fermions? They don't see this kind of mishmash of structures. Why is it that you see it? And we believe the answer lies in the parent ferroelectric. Parent ferroelectric, I've just got 2 or 3 minutes. The parent ferroelectric type has one stable polarization orientation and 6 variants at the most. Bismuth ferrite has 8 variants, so it has got all the more degrees of freedom compared to lead type. I think that's one of the reasons why it kind of forms all these different kinds of topologies. So obviously, just doing PFM is never enough. So nowadays, even if you want to kind of just say something very mundane, like I'm growing my films epitaxially, the referee will say, I want an aberration corrected stem image. So here's an aberration corrected stem image that shows displacement mapping of the individual structures. And if you look at the paper, so we had a lot of difficulties with one particular referee who said, oh, you're cherry picking data and showing only those regions which are showing these structures. So we actually showed in the paper, in the supplementary section, there's a lot more information than this paper. You see there are like so many sections. We've shown different kinds of domains. It's all over the sample. Now, final piece, and this is something that is really incredible PFM quality, but sadly, this is in the supplementary information of the paper, is that Peggy, the postdoc, was able to image different types of individual solitons and show that we have indeed center divergent and center convergent kind of structures. And that length scale is of the order of 20 nanometers. So this is really, this is PFMing at the absolute highest level, and it requires years of experience, patience, and talk. I believe talking to the instrument, communicating with the instrument, and taking it. So what's our next step? We're going to use this technique called tomographic PFM now. We already started working where we're going to use mechanical pressure to start manipulating these topologies. We want to see if it changes the conductivity and things like that. And I think the next year you will see some more papers come out of my group. Okay, so that's my last slide. I've shown you finally that if you do mechanical and electric field boundary condition engineering, you can get some really nice topological structures. Anisotropic epitaxy, that's what we are calling the 310 approach. Anisotropy because one side imposes a plane, the other side imposes an in-plane strain, and the other side doesn't. We have some really nice anisotropy on the manganite family system using this technique, and somebody, I think Bhagwati, he wanted to take a look at those samples. I'm very happy that he can find some use for that. We are still trying to understand more about these solitons. Why is there such a range of entropy in this system? They are not as large as the fermions that the Fagnet guys show, or even the type 2 multiferroics people show, then 3 to 5 nanometers, which is nice for devices, but 3 to 5 nanometers is a pain in characterization. So if you get something like 50 nanometers to 100 nanometers, characterization becomes nicer. Okay, so and finally, what I didn't go through, but it is in the paper, the detail is that polarization goes right into the dielectric layer. So you have new ways to understand interfaces using microscopy in this system. So with that, I will thank you for your attention. I'm sorry I went a little bit over, but it's not just throwing data. I also wanted to inspire students to think, sometimes you have to think differently from your supervisor. In fact, think most of the time differently from your supervisor. Because I told this to the morning guys, right? If you think the same way as your supervisor and you know the same as your supervisor, why should you get a PhD? Your supervisor should get a PhD. So one of the criteria in my group at least is that you need to know more than me to graduate. Only then I will let you do it. Thank you for your attention. I'll take any questions that anybody has still any interest. Okay, so it's slightly bismuth deficient. So it's a p-type.
How do you call it that you said you had large substrate distance?
Yes.
Have some
Yeah, so we enrich the target by at least 20%.
Have you seen any dependence on the effect of fluence? By changing the fluence, also you can get very low growth rate of having to.
But the fluence, it's not just the fluence. I don't have a physics answer. I have an angularity answer. It's also what happens in the travel time with the energy of the part. So when I said we can get this growth with very low fluence and very low growth rate, people with shorter distance have tried it. They've actually reduced the fluence quite a lot, but they cannot get it. Lane has tried this. You can't get this.
There's something called a stopping distance of the.
Yeah.
Moon actually stops after a certain distance. So it might not be within the plasma region as such. It might be just.
Possibly. I have really done the kind of physics, and I'm quite happy for you to analyze our plume and go for it. Unfortunately, the business is like you get some nice data, you write a paper, you have to get on to the next thing, write a paper. It's like a cycle, you got to keep pushing.
And,
Can we have a discussion outside, because there's another event in the physics department, they're going to stream them at 5:20. So I don't want that to be there. We can have the discussions outside the room. So sorry about it.
No problem.
Yeah, all questions we can go.
We can have
This is answering question like 50 rupees per question by outside. Inside is free, outside is 50 rupees per question.
All that is in here. All right, wait, you have to clap. Give it. Lecture and inspiring our students.
Only happens see, this happens only like Eastern countries. It's really great. In Australia, US, nobody cares.
I know, right? Be care. All right, the Chandrayaan gun, guys. We'll take it.